Part 2A is looking at one-way repeated measures ANOVAs in SPSS. I have laid out an example of data for you. Our purpose is that we have a researcher who wants to understand how exercise might reduce the risk of heart disease by measuring concentrations of C-reactive protein, or CRP, as we will refer to it in the rest of the example. If we look more into the methods, the researcher recruits 10 subjects to undergo a 6-month exercise training program. So the intervention has been identified as an exercise training program. CRP concentration is measured at 3 different stages within the 6-month period. So the exercise portion, I've highlighted that up here in yellow, so that matches our independent variable. The exercise is the intervention. What we're doing though is we are creating time periods. So pre-interval is kind of, or pre-intervention is like our baseline measurement with 0 exercise. Then we're saying at 3 months, somebody has accumulated enough hours of exercise that maybe it affects their CRP concentrations. And then at 6 months, our post-intervention, we measure again. And at 6 months, someone should have had more exercise than they had at 3 months, so it should be greater than the pre-intervention. So although the categorization, so that really weird, even though the categorization, anyways, even though it is based on time, it's still related to the fact that each time point has accumulated more exercise and more exercise as we go. So exercise, or the effects of exercise, are still going to be the independent variable as a progression of time. And then the CRP concentrations are what we are actually measuring. I believe this example, the units are in millimoles, and higher concentrations are associated with a higher risk of heart disease. So that's how we get kind of this relationship that's mentioned in the purpose statement. But once we've identified our variables, we can set up the test in SPSS. And the different thing about repeated measures is that every single level of your independent variable, or variables when we have more than one, each level gets a column in SPSS. Different from when we had independent measures or independent samples, where we assigned a label to each level, and then that all of the labels went into a single column. Or if we had 2 independent variables that were between subject factors, they went into separate columns. We don't have labels for repeated measures. Reason being is that when we actually flip all of this into the data view, remember the rows in the data view are going to be subjects. And if people are measured more than one time, everybody should have more than one measurement in their respective row. For this example, we had a pre, a mid, and a post measurement. So we should have 3 identified variables. Each of them is going to be representing the CRP concentration that was measured at that time point. So all of our measures should be listed as scale. Okay. So when we actually expand it into the data view, it would look something like that, which I think sometimes freaks people out, and it makes it difficult to figure out what your independent and dependent variables are if you're just looking at the data. But each level, pre, mid, and post, gets their own column in the setup. Once we have our data set up, similar to last week, we're going to assume we have a normal distribution and no significant outliers for our dependent variable. This is kind of our process that we're going to go through for the test. So the first thing is to set up the test. And then all hell breaks loose between 2 and 5. But setting up the test isn't that bad. We go to Analyze, General Linear Model, and then Repeated Measures. So both the one-way and the 2-way repeated measures ANOVAs get run through this pathway. Next week, when we do mixed factor ANOVAs, when we have one between and one within factor, independent variable, we also use this pathway. So repeated measure, it's a very versatile test or analysis in SPSS. And we use it whenever we have a within subject independent variable. Doesn't matter if there's one, doesn't matter if there's multiple. You could have one independent variable, but a lot of dependent variables, and we still could run the same test. So that's kind of a nice thing because one pathway is a lot easier to remember than multiple ones. But once you click on that analysis, you're going to be asked to identify your within subject factors. There's a naming box up here, which you kind of just use as like a general name for your variable. So we had different time points. So the example here is time, and there were 3 levels: pre, mid, and post. Once you've identified those 2 components of your factor, you click on the add button, and then the factor gets put into this box. In the measure name portion, that's where you put the dependent variable name. You click add, and then it puts it in the box, which I didn't have enough room for 3 screenshots, so this is where we're at. Once you have your levels defined as well as the dependent variable you've measured, you click define, and that will take you to the actual repeated measures setup. I know this looks kind of intimidating, but this was a really great outline that I found online, that if you look closely, there's arrows going to the right parts of things, so it generally makes sense. But in the variable box, we have our pre, our mid, and our post measurements. Up in here, it says within subject variables, the variables you defined in the previous window are going to be in parentheses. So for a one-way ANOVA, you're just going to have one independent variable. And then the number of levels that you specified will be counted downwards as you move through the variable box. CRP is just referring to the dependent variable that's attached to these levels. So I've run repeated measures, two-way repeated measures ANOVAs with multiple dependent variables before, so that's when the measure name really comes in handy. But we can see here, pre, we can assign to a value of 1, mid, we can assign to a value of 2, post, we can assign to a value of 3. So basically we just highlight these, press this button, chuck them in there, and then we can start setting up like our estimated marginal means, as well as any other calculations we might want. So EM means is where we set up our post hoc tests. The setup of these is going to be the same as what we did for the two-way independent ANOVA last week. We just don't have an interaction effect yet because we don't have multiple independent variables. But we'll move time into the display means for box, and then compare our main effects using a Bonferroni adjustment. Click continue, and then that ends up taking you back to the main repeated measures dialog box, which you'll then click the options button, and then we're going to choose descriptive statistics, which will give us our means, our standard deviations, the number of people that we have per group based on how we, actually it's more the number of measurements we have per level of our independent variable, but same sort of idea. I always get the question in this class, why isn't homogeneity tests checked? We only check this when we have a between subject factor. So if there is no between subject independent variable, this box does not get checked. So for repeated measures, pure repeated measures, ANOVAs, we're just going to do descriptive statistics and estimates of effect size. Click continue, and then that'll take you back to the repeated measures dialog box. Click OK, and we get an output. The first thing we have to do is check our assumptions. So again, the assumption we kind of add on to repeated measures is sphericity, which we assess using Machli's test. And you'll remember I had like a flow of things going on. This is what the table actually looks like. So we have our within subject effect time that we defined had 3 levels. And sphericity, again, looks at the differences of the variances of each of the levels of that time point. So we look at the difference between the variances of the pre-intervention and the mid-intervention, the differences between the variances of the mid and post, and then differences between the pre and post. If our variances of our differences are relatively equal, then we usually will get a p-value greater than 0.05. In this scenario, we have a p-value of 0.043, which is less than 0.05. So this would be an example of when we have violated sphericity. If p is greater than 0.05, we kind of just like accept that we've assumed sphericity, and then we go straight to the ANOVA table. If we have violated it, like in this case, we can argue that the variances of the differences between all of our time points are not equal. And then we have to do a couple of extra steps. So that's where this greenhouse geyser epsilon, hopefully those 2 words are ringing a bell from what I just said about 20 minutes ago. But we have to consult this portion of the table. So in Machli's test, again, only if sphericity is violated, we look at our greenhouse geyser epsilon value here. And there are certain criteria that we have to meet in order to determine which adjustment we need to apply to our samples in order to not have the unequal variances anymore. So if this value in this box is less than or equal to 0.75, we end up using the greenhouse geyser adjustment. So that would be the case for this example. However, if it was greater than 0.75, we end up using the Hune-Felt adjustment. So that's what GG and HF stand for. Okay. So now we've checked our assumption. We know we have violated sphericity for this particular example, which will help us in figuring out how to interpret our ANOVA results. So that's the next step in our process. I have a couple of slides that give us 2 different scenarios. So when you're going through your outputs and you're like, I violated sphericity, or I met sphericity, then you know which slide to go to. So this is a scenario if we have assumed sphericity. Let's say that our Machli's test gave us a p-value greater than 0.05, and we said we have equal variances of the differences. In the ANOVA table, which we call the test of within subject effects table, we have our condition, which is time, and then it's dinner time, sorry. And then we have sphericity assumed with the greenhouse geyser adjustment, with the Hune-Felt adjustment, and then the lower bound adjustment, which we don't use in this class. But we had determined, let's say hypothetically, that our Machli's test had a p-value greater than 0.05. That would tell us, go to the sphericity assumed row, and then this is the p-value you would report for the main effect of the test. So in this case, p would be reported as less than 0.001, which is a significant p-value in comparison to 0.05. The null hypothesis for the main effect of our ANOVA is that our independent variable has no significant effect on the dependent variable. So because we have a significant p-value, we reject that null and we say that exercise has a significant effect on CRP concentration. If you wanted to extend that a step further, it likely also has an effect on the risk of a person getting heart disease. So again, hypothetical slide, it's not actually what happened in our data set. What actually happened in our data set was that we violated sphericity. So we had determined when we looked at the greenhouse geyser epsilon value that it was less than or equal to 0.75. So we then said, we're going to use the greenhouse geyser adjustment. That's what this is here. So then we would read the p-value under or across the row for greenhouse geyser. So p would be less than 0.001, and our interpretation would be exactly the same as the previous slide, that exercise has a significant effect on CRP concentration. Or you could also say there's at least one significant difference between time points. But again, these would be the results that we actually accept for this example. One more slide just in case we violated sphericity, but we had a greenhouse geyser epsilon that was greater than 0.75. Then you would read this row, not the yellow one where my red box is. And coincidentally, all of our p-values are exactly the same value, so the interpretation would be exactly the same. Okay, questions on sphericity? Very fun concept. Not really. Okay. We're kind of like, this is the thick of the one-way repeated measures ANOVA, is figuring out if you met sphericity or if you violated it. Once you figure out if you've met or violated, and you figure out your main effect, in all of these cases, whether we had met or violated sphericity, we have significant p-values. So does anybody know what that means? I see a chat. Do we need to know anything about error? No. This is just the part of, like, this is the mean square. So when we went through our calculation for the F ratio in our ANOVA table, remember I told you guys we have the condition row, that's like our time row. We had a subjects row not included in SPSS. The error row included in SPSS, and then a total row not included in SPSS. So the error part just goes into the calculation of the F statistic, which is why it exists in the table. Yeah. But does anybody know what we do if we have a significant main effect? Back to my original question. What's the next step? Pairwise comparisons with a sad face. Oh no. Yeah, we would look at pairwise comparisons. So only if your ANOVA is significant, you do post-hoc tests. That is the case for our example. Lucky for us, we only had 3 levels. So we're only looking at the comparisons of the pre and mid, the pre and post, and the mid and post CRP concentrations. Okay. Remember that we have redundancies in our table, so that's why these 2 rows are highlighted, right? The difference between 1 and 2 is the same as the difference between 2 and 1. Same pair, okay? They have the same p-value, they have the same mean difference. One of them is just negative and the other one is positive, right? So the order that they're listed in the columns is the order that they are subtracted from one another. In this case, time point 1, or our pre-CRP measurement, minus our mid-CRP measurement, ends up with a positive mean difference. That indicates that we had a higher mean CRP concentration at the pre-measurement than we did at the mid-measurement. Same thing could go for pre versus post. But we get p-values for each of these comparisons, and then we can say what our significant pairs are in this case. For our particular p-values, there is a significant difference between the pre and the mid measurements, and there is a significant difference between the pre and post measurement, as well as a difference. Nope, just kidding. I lied. I was going to say between mid and post, but it's 0.054. So didn't quite make the cut. But once we figure out what our significant pairs are, we can translate those into an interpretation, which I start varying my wording a lot throughout this week. Last week, it was like a nice like nudge into interpretation. So I tried to stay on the more consistent side. This week I kind of mixing around. So if maybe I did something last week didn't make sense, it'll make sense this week. But we can interpret our significant pairs as there were significant differences between pre-intervention and mid-intervention, as well as the pre and post-intervention. CRP concentrations. I put this in parentheses at the end where I just noted what the non-significant differences were, but you don't have to add that. It's just there so you can see that it was not significant. But yeah, pairwise comparisons. And that's the end of the ANOVA. Woo! Questions on ANOVA? Take another sip of water. Okay, no, there we go. No effect size. Ha! There it is. There is an effect size. I'm so sorry. Oh, virtual hugs. Oh, tears. You guys are making me sad. Okay. Effect size. Yeah, there is one. We still are going to call our one-way effect sizes omega squared, because that's what is automatically included in the outputs in SPSS. So that's kind of nice. I also do have a formula if you wanted to hand calculate, but honestly, once you get to your exam, that's kind of up to you how you calculate stuff. You'll have all of the formulas at your disposal. So if you had to use them, you just kind of plug and chug as needed. But the interpretations are exactly the same as what we had last week. The formula just changes a little bit because of the within subject factor. So we take K, which is the number of levels of our independent variable, minus 1, multiply that by the F statistic in our ANOVA table, minus 1. Do the same thing in the denominator, and then add the product of the sample size times how many levels we have. Based on the data that we have, we had 3 groups, so that's where we get 3 from, minus 1. The F statistic came directly from our ANOVA table. And if I actually scroll back to this one, oh, that's sphericity. That's still sphericity. There it is. So we had sphericity. Hypothetically, that was sphericity assumed. This is the one we actually looked at. So this F statistic, 26.938, if I take us back to the effect size calculation, that's where that value came from, the ANOVA table. We do F minus 1, repeat the numerator in the denominator, and then multiply by the number of levels times how many subjects we had. So the 3 and the 10 are kind of backwards, but it's still the same product. This gives us an omega squared of 0.63, which we can interpret as a large effect size between the differences of the time points or between exposures to exercise. Either one probably would work. Question in the chat is, where is 10 from? This is the sample size, N. 3 is K, the number of levels. Let's take a break. But I'll keep answering questions. But if you want to go away for like 5 minutes, that's fine. I'll keep recording. Question in chat: does the F stat need to be for this specific assumption we assumed? Yes. In this particular example, all of the F values were the same in the ANOVA table. So like 26.938 is consistent through here. That's not always the case though. So F will change based on the degrees of freedom adjustments that happen. And so you'll make sure if you assume sphericity, you take the F from sphericity assumed row. If you violated it, you take it from whatever adjustment you ended up using. Yeah. We also have a partial eta squared in this, but I've been trying to read up on which effect sizes are better, and generally people don't like to use partial eta squared effect sizes for one-way ANOVAs. I'm guessing it has to do with how the calculation is done, but